1.4. The mass spectrometer. The mass spectrometer is the most useful instrument for the accurate determination of relative atomic masses AR. Relative atomic masses are measured on a scale on which the mass of an atom of carbon-12 is defined as exactly 12. No other isotope has a relative atomic mass that is exactly a whole number. This is because neither the proton nor the neutron has a mass of exactly 1. Relative atomic mass AR is equal to average mass of one atom divided by 1/12 mass of one atom of carbon-12, where relative molecular mass MR is equal to average mass of a molecule divided by 1/12 of mass of one atom of carbon-12. The mass spectrometer determines the mass of separate atoms, or molecules. Mass spectrometers are an essential part of a chemist's toolkit of equipment. For example, they're used by forensic scientists to help identify subjects, such as illegal drugs. There are several types of mass spectrometers, but all work on the principle of forming ions from the sample and then separating the ions according to the ratio of their charge to their mass. The type described here is called a time-of-flight TOF instrument. So, what happens in the time-of-flight mass spectrometer? In outline, the substance in the sample are converted to positive ions, accelerated to high speeds, which depend on their mass-to-charge ratio, and arrive at a detector. The steps are described in more detail below. So first you have vacuum. The whole apparatus is kept under a high vacuum to prevent the ions that are produced from colliding with molecules from the air. Ionization. Two types of ionization are described here. In electron spray ionization, the sample is dissolved in a volatile solvent and forced through a fine hollow needle that is connected to the positive terminal of a high voltage supply. This produces tiny positively charged droplets that have gained a proton from the solvent. The solvent evaporates from the droplets in the vacuum, and the droplets get smaller and smaller until they may contain no more than a single positively charged ion. In electron impacts, the sample is evaporated and high-energy electrons are fired at it from an electron gun, which is a hot wire filament with a current running through it that emits a beam of high-energy electrons. This usually knocks off one electron from each particle, forming a 1+ ion. Acceleration. The positive ions are attracted towards a negatively charged plate and accelerate towards it. Lighter ions and more highly charged ions achieve a higher speed. Ion drift. The ions pass through a hole in the negatively charged plate, forming a beam and travel along a tube called the flight tube to a detector. Detection. When ions with the same charge arrive at the detector, the lighter ones are first as they have higher velocities. The flight times are recorded. The positive ions pick up an electron from the detector, which causes a current to flow. And finally, data analysis. The signal from the detector is passed to a computer which generates a mass spectrum. The mass spectrometer can be used to identify the different isotopes that make up an element. It detects individual ions, so different isotopes are detected separately because they have different masses. This is how the data for neon, germanium and chlorine isotopes were obtained. The peak height gives the relative abundance of each isotope, and the horizontal scale gives the MZ ratio, which, for a singly charged ion, is numerically the same as the mass number A. Mass spectrometers can measure relative atomic masses to 5 decimal places of an atomic mass unit. This is called high-resolution mass spectrometry. However, most work is done to 1 decimal point. This is called low-resolution mass spectrometry. The low-resolution mass spectrum of neon is shown in figure 3. This shows that neon has 2 isotopes with mass numbers 20 and 22, and abundances to the nearest whole number of 90% and 10% respectively. From this, we can say that the neon has an average relative atomic mass of 20.2. When calculating the relative atomic mass of an element, you must take account of the relative abundance of the isotopes. The relative atomic mass of neon is not 21 because there are far more atoms of the lighter isotope. Another example is the mass spectrum of element germanium, which is shown in figure 4. Chlorine has two isotopes. There are chlorine-35, which has with a mass number of 35, and chlorine-37 with a mass number of 37. They occur in the ratio of almost exactly 3:1. So there is 75% of chlorine-35 and 25% of chlorine-37, which naturally occur in chlorine gas. The average mass of these is 35.5, as shown below. So you have the mass of 100 atoms, which is 35 times 75, plus 37 times 25, which gives you 3,550. So an average mass will therefore be 3,550 divided by those 100 atoms. So you get 35.5. This explains why the relative atomic mass of chlorine is approximately 35.5. Space probes such as the Mars rover Curiosity carry mass spectrometers. They are used to identify the elements in rock samples. The Huygens spacecraft that landed on Titan, one of the moons of Saturn, in January 2005, carried a mass spectrometer used to identify measure the amounts of the gases in Titan's atmosphere. After landing, it also analysed vapor samples of the surface.